Okay, this video is optional, as in this will not be tested on the AP test, but if you are interested into the proof of the intermediate value theorem, here's a quick sketch. So we're going to use a few properties that you might not know about. It will be good if you go check them out before the video, since there's a lot I might need to explain if you don't know. So we're going to use the property of completeness of the real numbers. This is a part of analysis. So if you're into that as well, you should probably look this up as well. Okay, so completeness of real numbers. What this implies, one of the properties it implies, is that if we have a non-empty subset of R, non-empty subset, let's call this S, which is bounded from above, then it has a least upper bound. We will call this the LUB. So what this means is that, for example, have a subset, it's for example here. We have a function that ends here, and then it's bounded by here, then we have a least upper bound. So first of all, if we have a function that comes from A all the way to B, then for a value k in the range of fa, fb, here we will just presume that fa is smaller than fb. It's pretty the same the other way around. So for a k in between, let's call this k. Then we're going to make the subset of R. Subset of R. Subset of R, we're going to call this S, which is defined as all the values in the function from a to b that are smaller than k, f, x, or equal to k. So now, since the real numbers are complete, then we can find a least upper bound of this subset. This means that we can find a C in this subset such that such that all the other terms in the subset are smaller than or equal to fc. Now we will try to prove that fc indeed equals to fc equals to k. Now since c is the least upper bound, this means that for any epsilon bigger than 0, there exists a delta bigger than 0 such that when x minus c smaller than this delta, fx minus fc also smaller than this epsilon. So hence fc is in the range of fx minus e, fx minus epsilon, and fx plus epsilon. Therefore, fc is smaller than fx plus epsilon, which is, since this is bounded by k, remember, which is smaller than or equal than k plus epsilon. Now since we made the subset that is smaller than or equal to k, then it's pretty obvious we can also make the subset that is bigger than or equal to k. If you're interested, you could prove this by yourself, but basically what this shows is that fc is also bigger than k minus epsilon. For here, it's also for any epsilon bigger than 0. So what this means is that fc is in the range k minus epsilon, k plus epsilon. We can make this epsilon be any number we want, so we can make this super small. And when it is super small, note that fc is actually exists. It is existing as a value in this function, therefore fc equals to k. And we have proved the intermediate value theorem, which if we scroll up says that there exists a c and ab such that fc equals to k.